Hello, welcome back. Okay, this video is going to be discussing the 5 probability rules, the first 5, okay, the first 5 probability rules, and let's get started. Okay, so the first rule for probability is that it has to be between 0 and 1. This is how we write it, okay? So basically it's going to be a decimal between 0 and 1. Now it can be 0. Okay, so a 0 would be something like this. Let's say the event is blue or red. Okay, and this could happen 50% of the time, and this could happen 50% of the time. And then I say, what's the probability that it's orange? And you would say 0. Okay, now it could be uh, a little. So that's the case where it's 0, and this is another. Let's call this sample space 1. Let's call this sample space 2. This is a little less interesting, but let's say we have one outcome in our sample space, okay, and that is, okay, let's say that is purple. And then I ask, what's the probability that you select the purple? Let's say I put 10 purple slips in a bag. And I say, what's the probability you're going to pull one slip? You're going to reach in that bag and pull one. What's the probability that that's purple? Well, there's a probability of 1. Okay? And of course, these decimals could be changed into percents. Okay, in case you're not sure, this is a number between 0 and 1. So if you look at this number line, this is stuff that I just overlooked because you learn this stuff in, you know, other algebra classes or some math class. Okay, so this is a number line. So any one of these numbers, like this could be 0.35. So to change numbers to percents, okay, we just multiply it by 100. Okay, so to change this to the percent, I just move the decimal 2 to the right. So 0.35 is equivalent to 35%. Okay, so if I said, oh, I got 0.8, 0.8's over here. Okay, so 0.8 is equivalent to 80%. Okay, and vice versa. If you want to go from a percent to a decimal, you move the decimal 2 to the left. Okay, this is very important. The sum of all probabilities, the sum of the probabilities of all outcomes must equal 1. Okay, so another important thing to note is not all outcomes are equally likely sometimes. Okay, for example, um, let's just I'll just make, let's say we're picking colors from an M&M bag, and of course all colors aren't equally distributed in the bag. So let's say we have blue, red, and green in a bag, and the company says, well, 60% or zero point 0.6 of them are blue and 0.3 are green. Well, these are the only outcomes. These are my 3 outcomes. That's one outcome, that's one outcome, and one outcome. Okay? So the sum of the probabilities of all outcomes must equal 1. So that tells us, okay, so that this one here must be 0.1, because this outcome plus this outcome plus this outcome must equal 1. Okay? So that's the sum of all probabilities must equal 1. Okay. Now let's get to the complement. Okay? The probability of event happening is 1 minus the probability that doesn't happen. Okay, so let's go to our blue. Let's say there's only 2 colors, blue and green, in a bag of M&Ms. Okay, and let's say this is 0.8, and if these are the only 2 outcomes, we know what this green is. The green must be 0.2. Okay, so let's look at this. The probability of an event happening is 1 minus the probability that it doesn't happen. So I could say this. What's the probability that you get a blue? The probability that I get a blue, okay, is 1 minus the probability that I don't get a blue, which is a green. Okay, so for example, let me cross this out. These are just complement rules, okay, since two have to be this is true because both of these have to equal 1. Okay, so this rule's kind of a extension onto this one. Okay, so what's the probability of blue? Well, if I don't know blue, it's going to be 1 minus green. So the probability that it's blue equals 1 minus the probability that it's not blue. So I could do blue and put a little c on here. That's what this means, the complement. Okay, so let's do that. The probability of blue equals 1 minus, what's the probability that it's not blue? Well, if it's not blue, then it has to be green. So it's 1 minus 0.2, which is 0.8. Okay? So you could say there's different ways you could do it too. But we'll do examples of this later. But just know that the complement is the event is the event not happening. This is the event, and a complement is the complement, or the event doesn't happen. So here it happens. Here it doesn't happen. Get comfortable with this notation. Okay, we use this a lot. We use this a lot. Okay, and we'll do examples, harder examples to show you. Okay, now we're getting to 4, so this gets a little more complicated. For two disjoint events, A and B, okay, the probability that either A or B occurs is the sum of the probabilities of both events. Okay, and here's the notation. But let's talk about disjoint for a second, and let's talk about what this means, because you're not going to understand it if you don't know what it means. Disjoint, or we also call it mutually exclusive. You have to know both terms. You must know both terms. They mean the same thing. Okay? This is when two events do not have any outcomes in common. Okay? When two events do not have any outcomes in common. Okay? So if you remember this, you add with these ors. So whenever you see an or problem, or sometimes this is like either A or B happenings, you sum the probabilities of both events. Okay, and I'll give you an example, and you'll see right away. So we'll go back to the M&M problem. Okay, so I have these 3 colors and an M&M bag, and the company tells me that we should expect 50% blue, 30% orange, and 20% red. Check to make sure this is good. 5, 6, 7, 8, 9, 10. That's 1. Okay. Alright, so now I'm going to say, what's the probability that you're going to reach in the bag? Pick one. That's my trial. Pick one. Okay? That's my trial. What's the probability that it's a blue or an orange? Okay? So are there any outcomes in common? Do they have outcomes in common? No. It's either blue or it's orange. There's no blue and orange at the same time. Okay, so a lot of you guys just might see it. What's the probability you pick a blue or an orange? Well, it's just 0.5 plus 0.3, which is 0.8. So if you solve it, okay, that works. Okay, so I'm going to show you an example where it doesn't work. Okay, so say the probability of that somebody owns an iPad is I'll say 60% or 0.6, and the probability that somebody owns an iPhone is the same person. Same person. One person. One person. So an iPhone is point 0.4, let's say. All right, let's make it 0.5. Okay, 0.5. So 60% chance that this person owns an iPad, and uh, 50% chance they own an iPhone. So what's the probability that if you pick somebody that they own an iPad or an iPhone? Okay, so outcomes in common means can one person own both? Can one person own both? That's a yes. Okay, so if one person could own both, then they're not disjoint. There's outcomes in common. So this is not 1.1. Okay, so next chapter we're going to deal with this problem. We're going to deal with this. Okay, when outcomes are not disjoint. Okay, and I'll show you what it looks like on a Venn diagram, because we like using visual. Okay, so here would be my sample. This is my sample space. That's my S, and we denote events by circles. So this is the event A. So these are all the outcomes in A, and this is this is event B. So, and these are the outcomes in B, and these are all the outcomes in A. Okay, so you see how they don't touch? If they don't touch, that's considered disjoint, or as a lot of times I use, mutually exclusive. I feel like this is misspelled. Let me look real quick. Doesn't look right. Yep, it's misspelled. Okay, and now I'll add a U there. So I did it again. Mutually exclusive. Okay? Alright. So our last rule, okay, is independent. So let's talk about independence for 1 second. Now we will have a way to check specifically if two events are independent. Independent events. Okay, when the outcomes of one event do not affect the outcomes of another event. Okay, when the outcomes of one event do not affect the outcomes of another event. Okay, so generally you're gonna have to get good at telling if two events are independent or not, and generally you could tell. So one case could be like, okay, so the event could be something like the average of student scores. Okay, and another event could be if the student is left or right-handed. Okay, so do you think the outcomes of the student being left or right-handed affect their student scores? If your answer was no, then these two events are independent. Okay, so we learned about this earlier on the 2x2 tables. You have to be comfortable with just seeing two different events and trying to determine if those two different events, if the outcomes of one affect the other one. If they don't, then they're two independent events. And if they're independent, then we can multiply their probabilities. Okay? Do not look at a Venn diagram and try to determine independence. You can't. We do have a way to determine if disjoint events are independent, okay, and vice versa, but that's going to be a whole nother video, okay? That's a pretty important concept that a lot of people miss on the AP, and it's actually good to know, okay? Because you always want to get things correct that you think other people are going to miss. That actually helps you out. Okay, so I'll just give you a quick example. So flipping a coin, a fair coin. Okay, that'll be A. And B will be rolling a fair six-sided die. Okay? So I'm gonna say A is the event of getting a heads, and B is the event of rolling a 6. Okay, so I'm going to say what's the probability of A happening and B happening. So let's say I flip a coin and roll a die at the same time. Okay, that's essentially the same thing. If I flip a coin and roll a die, what's the probability that I look down and the coin says heads and the die says 6? Okay, so let's check to see if they're independent. Does flipping a coin affect what the outcomes on rolling a die? No, so they are independent. You always have to check for that, okay? Because if they are independent, then it's not the same probability. Okay, so it's gonna be the probability of A times the probability of B. So the probability of A, which is getting a heads, is 0.5. The probability of getting a getting a 6 is 1 over 6. So if I multiply this through, it's 0.5 times 1. I'm gonna, mathematics. If this 0.5 could just be written as a fraction, so you'll go across the top and across the bottom. So it's 0.5 over 6. Okay, and I'll go ahead and bring out my calculator. So it's 0.5 divided by 6, which is 0.083, which is, okay, so approximately, move the decimal to the right, 8.33% chance. Okay, and what this means is if you sat there and flipped a coin and rolled a die 100 times, you'd expect this to happen about 8 or 9 times out of those 100 tries. Okay, that's another way you should think about probability in the empirical sense. Okay, we're doing all this on the theoretical. Okay, so those are the 5 rules. Next chapter is going to deal with when two events are not disjoint. Okay, if two events are not disjoint, which means that they're joint. Okay, so if these were the outcomes in A and these were the outcomes in B, you could see that they do meet. Okay, so these are the outcomes, and here this is A and B. These are the outcomes that are in common. Okay, so that's that. I know this ran a little long. I'm sorry, and hope you spend the time and watch it. Have a nice day.